Okay. All right. So we are on lecture 21. So I know my TA has still got a little bit of stuff to grade. There's a few outstanding assignments, but exam 1's graded and it's posted. So homework 5.3 and 5.4 are being graded. Hopefully the homework that you just turned in regarding the concentrated moments, hopefully that one was pretty straightforward. Anybody have any trouble with that? Okay, good. All right. Let's talk about this. So you'll notice I threw this up here. So just so everybody is aware, you've got homework 5.5 due today, which was the homework on concentrated moments. You're going to have 5.6 due on Wednesday. That's going to revolve around what we do today. That's the problem with the internal hinge. And then on Wednesday, here's what we're going to do on Wednesday. On Wednesday, we're going to put a bow on shear and moment diagrams and sort of wrap this topic up because I want to discuss shear and moment diagrams for frames, and I want to discuss the topic of using analysis aids, sort of pre-derived formulas for shear and moment diagrams. I want to discuss how you use those, some of the pitfalls associated with them, and so we're going to talk about that on Wednesday. On Friday, what are we going to talk about? Nothing, because we're not going to be here on Friday, right? We have our fall break. So Friday, we don't have any class, and I'm not asking you to turn anything in. So the only thing that's going to happen, though, is on Monday, the first submittal of your project's due. But I usually am not one of those guys who's, right when you come back, here's something due. But I think most of you have already started working on the submittal, and it's really not a lot of work, and you've had, like a month or so to work on it. So that's going to be due Monday when we get back. And then I'm giving you a homework this day, and I'm having it due the following Wednesday. It's not like the homework's going to be super, super long. I just really didn't want a homework assignment due the day you got back. So, sound good? All right, any questions? All right, everybody get the code. All right, okay. Let's jump right into it. Let's jump into frames, or sorry, not frames. The internal hinges. Sorry. Okay, let me get my keyboard off here. So I am going to skip through this first part of the slideshow because we did already talk about this. We talked about how to compute internal indeterminacy for beams and frames. So this part, we had already talked about how, this is what we talked about on Friday, about how we had discussed external indeterminacy and internal indeterminacy for trusses. And then for beams and frames, the formula is a little bit more involved, but it's not really difficult. It's more involved because frame or beam type flexural elements just have more going on. They can have axial, shear, and moment responses. So there's 3 unknowns for every member, and then there's 1 unknown for every support reaction. So the unknowns are 3m plus r, and then the known quantities are 3j plus EC. EC is for if you ever have an internal hinge, which we're going to have today. And then 3J is because every joint has to satisfy 3 equations of equilibrium now, not just 2. Again, I'm going through this part real fast because we talked about this on Friday. Any questions about this? Again, hopefully it's pretty plug and chug. All right, this is really what I want to talk about today, which is shear and moment diagrams for beams with internal hinges. Okay, and so I really want to make this point crystal clear. Okay, so the question is, how does the presence of an internal hinge affect your construction of a shear diagram or a moment diagram? And the answer is, it doesn't. Okay? So what I'm saying is, when you are constructing the shear diagram or the moment diagram, just ignore it. It doesn't matter. Okay? And I'm saying this because I guarantee you, if we have an exam problem and there's a beam with an internal hinge, there's going to be students that are going to try to assign some reaction to it or figure out some force. No, it doesn't affect the construction of the shear and moment diagram at all. So what does it impact? What's the point? Well, let's talk about a moment release, an internal hinge. When you provide an internal hinge into a beam, you provide an equation of condition. We use the fact that the sum of the moments are 0 at that hinge in order to solve for reactions. So those reactions that we get when we analyze the structure, those are the reactions necessary to satisfy not only the equations of equilibrium for the whole structure, but it also satisfies the equation of condition at the hinge. So when you get those reactions, they satisfy that. So those reactions should take care of any concerns that you have when you construct the shear and moment diagram. So once you get those reactions, pretend that hinge doesn't exist, okay? And if you do it correctly, you will see a very, let's just say the response that you'll see at that hinge should make a lot of sense, okay? Sound good? Everybody good? Now, like I said, we're going to do a start to finish problem in here, so I'm not giving you the reactions on this one like I have on some of my other examples. We're going to do a start to finish shear and moment diagram problem here. I say compute the support reactions. Maybe I should edit this and say and construct VM diagrams. For this beam, and so remind me, how many unknown support reactions are we going to have for this problem? How many? Say it again. 4, because we have 3 here at the fixed support and we have 1 here at the roller, okay? So we're not going to be able to apply solely equations of equilibrium, because equilibrium we only have 3 equations, right? We're going to need to use something else. And so what secret weapon of structural engineering are we going to need to break out in order to solve for this additional reaction? We're going to have to cut a section, right? We're going to have to break out the samurai sword or lightsaber if we happen to be sci-fi fans. We're going to have to cut a section. And where are we going to cut a section? Through the hinge, right? Okay, so let's break out the notebook. Let's see what we got. All right. Okay. All righty. Okay. So, oh, it would help if I had my little handy dandy notebook right here. The notebook with all the answers. Okay. So if we start just identifying our unknown reactions, okay? So we know we're going to have a reaction here. We'll call that BY. And we know we're going to have a vertical reaction here, AY. Okay? We know we're going to have a potential horizontal AX, and we're going to have I'm drawing some pretty rough looking arrow tips right there. Call that MA. So those are our 4 unknown reactions. Now one of them we should be able to knock out pretty easily, right? Which one is that? AX. Because are there any horizontal forces anywhere on this beam? No. So what is AX? 0. Okay. So we'll just sort of put this up here. AX equals 0. Okay. So we got one of our reactions. So at this point, you all should have enough experience with computing support reactions that I think that you all should tell me what to do instead of me telling you what to do. So tell me, what do I need to do? Come. Take the moment about A? Well, we can, let's, what's that? Well, we can some moments about A. Let's do that. Let's see what happens. Okay? So if I sum moments about A, like I'm going to do it kind of roughly here. Okay? Am I going to have to consider AX? Am I going to have to consider AY? Am I going to have to consider this? So that's one unknown, right? Am I going to have to consider this? So if I do that, which I'm not saying I'm not going to have to, I am going to have to do that. But if I do it now, I'm going to have an equation with 2 unknowns. So it's not going to directly yield, like BY equals 4 or MA equals 6. Like I'm going to have an equation with 2 unknowns. So I guess my question is, I am going to have to do it, but is there something else I can do now to make life a little easier?
Section at the hinge and then look right.
Okay, all right, so let's cut a section at the hinge, okay? So let's cut a section at the hinge. All right, so we are going to have to sum moments today. We will. We'll just do it a little later, okay? So I'm going to cut a section at the hinge. Now, why look right?
Easier.
There's just less going on, right? And just make my life a little easier, right? So we're going to break out the samurai sword or lightsaber, and we're literally splitting this, this structure into two pieces, and I am only going to consider the piece on the right, okay? So what we'll do is we'll say, okay, so we'll consider section 1-1. We'll consider section 1-1 looking to the right. Okay? So okay. Tablet's getting a little toasty. All right. So if I'm cutting a section right here, I've got the roller reaction right here, and then the only load I see is the distributed load. So the distributed load is going to look something about like this. And then here is that. Okay. So at this hinge, I'm going to have a shear. Which way do I draw a positive shear, by the way? If I cut a section and look to the right, which way is positive shear? Up. You got to love like the long protracted answer. You're like, yeah, up. I meant up. I meant up. We're going to have an axial force. Are we going to have a moment right there? No. Why don't we have a moment? Because we're cutting the section through a hinge. That's the whole point of hinge, is that there is no rotational moment there at the hinge. Okay? Now, what is the length of this segment, by the way? 20. Okay. And then this is 3 kips per foot. So what do I do with that 3 kips per foot? Collapse it into a point load, and that's going to be 60 kips where?
10 feet.
10 feet from the section cut, or 10 feet from the right, doesn't matter. So we're going to turn that 60 kips, 10 feet. Okay. So tell me what to do. I have 2 unknowns here, 1 unknown here. Do I really care about these unknowns? Not really. You're going to see something here in a second, but I don't really care about them right now, do I? Okay, so tell me what to do.
Sum the moments about the cut.
Some moments about the cut, looking right, yeah. So we'll sum moments about the cut. Okay, and this should be pretty easy, right? Because I'm going to have what? 60 times 10 going like that, and then something times 20 going like that. By the way, what is that something going to be? 30. Yeah, that should be pretty easy to do in your head, right? So 60 kips, 10 feet. We'll call it BY. That should be pretty easy, right? I'm going to erase this because I want to make a note on something. Okay. So let's big picture this. Okay. I'm not going to do anything right now, but let's just big picture this. Now that I have by, what do I do? Tell me what to do. What would be my next steps? Now we can go back to the original structure and maybe some forces, some moments, do all that, right? With me so far? And then after that, I can then start drawing a shear diagram, draw a moment diagram, right? So, everybody with me on the big picture? Okay, what I am about to do has nothing to do with that big picture, but I want to do it for a specific reason, okay? I want to do this. I want to sum forces in the y direction for this little free body. I don't need this for the purposes of computing support reactions, but I just kind of want to do it. And you're like, why do you want to do this? We don't like structural analysis as much as you do, Dr. Mike, so why do you want to do this? Well, you'll see. Just trust me. All right, so what do I have going up? I've got V going up, and I've got BY going up. What do I have going down? 60 kips. Okay. So would you agree with that? Would you agree with the fact that the shear is 30 on this free body diagram? Okay. So let's just sort of take stock of that. So I'm going to put this here on the board. So note. V is plus 30. And by the way, what's M? 0. Okay. Okay. So let's just keep that in the back of our head. Let's just see if that becomes relevant a little later. Okay. So far, so good? Okay. Now, back to the original structure. Okay. So let's just go back to the original structure. We know that this is 30 kips, and we know that AX is 0. So everybody's right. We have to sum moments at A, but we're also going to have to sum forces in the Y direction, right? We're going to have to do that. So it's not really going to matter which one we do first, but I think what I'm going to do is I'm going to do it on the board to sort of prevent the scrolling, and then I'll transpose it to the notebook here in a second. So we're going to have to sum forces in the Y direction first, or we're going to have to do this, and then we're going to have to sum moments at A. I think it was Mr. Hartwell said let's sum moments at A, so let's do that one first. Doesn't really matter, but we'll do this one first. So if we sum moments at A, do I need to consider AX or AY? No. Do I need to consider MA? Yes. And that's going to be on that side, right? Do I need to consider the 90 kips? Does it generate moment at A? Which side of the table does it belong, left or right? And what's the moment arm? Right? Okay. The BY, I have the BY times 30 feet, or the BY times 30, BY of 30 kips. What's the moment arm for BY? 50 to 80, yep. Okay. And am I missing anything? Oh, the distributed load, right? So instead of breaking this distributed load into pieces, how much total length of the beam? 80 feet? So 80 feet at 3 kips per foot is going to be what? 240, right? So I'm going to have 240 kips times what? What's the moment arm going to be from A? 40 feet. Right? So that's going to be our summation of moments at A. Okay? So let's see if I can do some math here. So 90 times 50, that's what? 4,500? 240 times 40, that's what? 9,600. And that's 2,400. Right? So what do we got? We've got 4,500 and 9,600. What is that? Like 14,100? Right here, 14,100 foot kips. Did I do that right?
Yeah.
And that's going to be BY times 80 feet. Or sorry, nope. Ignore that. It's going to be MA plus 2,400 foot kips, right? So subtract, and I'm going to get MA is positive, what is that, 11.7? And then that's going to be like that. Did I do that right? So far, so good? Okay. Now, what about summing forces in the y direction? I'm going to have AY going up. BY is 30 kips. Here, maybe what I'll do is just to sort of make this a little easier to follow. Just do that. What's that?
Maybe it should be the other way.
Oh, you're right. You're right. Thank you. Yeah, no, you're right. It is. It's going that way. Whoopsie. All right, thank you. So we have AY going up, 30 going up, and then we have 90 going down, and what, 240 going down? Right? How am I doing? So AY plus 30 is what, 330? So what, AY is 300? So far, so good? Okay, so while you all are jotting that down, I'm just going to really quickly put that in the notebook so we all have it. So I'll be quick about it. I'll be quick if I can write. Sorry. I didn't want to do too much scrolling. All right. Okay. All right. So, everybody okay with this? All right. So, one thing I'm going to do because I am lazy is let me see if everything's going to cooperate with me. Is I'm going to, for the purposes of constructing the shear and moment diagram, all right, I guess I'll just redraw it. Is I am going to redraw the beam again because I want to be able to put the shear and moment diagram right under it. So let's see if I can do that. So okay, now there is a hinge in the beam, okay, so I think the hinge is going to be, I don't know, about like this. That's about where the hinge is, right? 60 feet over from the left or 20 feet over from the right. So keep in mind, for the purposes of constructing the shear and moment diagram, we're going to ignore that. Okay, we got that this reaction here was 30 kips. We have a vertical reaction here of 300 kips. We have this of 1,700 foot kips. And then we've got, let's see, I think we have a load right there, which is 90 kips. This is 3 kips per foot. Am I right? And then for labeling, this was point A, this was point B. So I think I'm going to call this C and D, just for the purposes of our discussion, just so that as we start talking about this, we all have sort of the same vernacular. Okay, shear diagram. Let's see if we can knock this out. This is going to utilize all of our skills to date. Okay. I like that. There we go. All right. So y'all know the drill. You tell me what to do. We're going to start at 0, but tell me what to do. Up 300, right? We pay attention to the vertical forces here. Okay. So so we're at 300. From A to C, what happens from A to C? Down 150. Okay, now how did you get 150?
3 times 50.
Yeah, 3 kips per foot over a distance of 50 feet, so it's 150. So if I'm at 300 and I drop to 150, that's going to put me at 150 right here. So what does that path look like? What does it look like to go from 300 to 150?
Negative slope.
Linear slope at a slope of?
Negative 3.
-3, because that's the load. So let me see if I can do better than that. I told y'all that having a straight edge would help, didn't I? See, there was a reason there. So what happens here at the 150?
Goes down 90.
Say it again.
Goes down 90.
Goes down 90 to what? 60. So maybe about right there. Okay, now what did I tell you? What do we do with this hinge at this point? Ignore it. So ignore the hinge. So just tell me what happens from C to B. Okay, so if I'm at, for how much total load? From C to B? 90. So if I'm at 60 and I drop down 90, where am I going to be over here? Negative 30. Okay, so see, I'm going to get, I am going to get this the way I want it. I think that's the best I'm going to do. So that's negative 30, and that's going to bring me back up to 0. And that, ladies and gentlemen, is the shear diagram. Now, Ashton noticed something, so. Oh, you all noticed it? Could somebody tell me, for the folks that didn't notice it, what is the shear right there? 30 kips. And where is that location? Look at that. It's crazy, isn't it? It's like statics works or something. No, I mean, in all seriousness, we cut a section and determine the internal response at the hinge. And the internal, that's what this is. Remember, shear diagrams are just cutting an infinite number of sections. So the idea is if you cut a section at the hinge, whatever the shear diagram says is that is the response. Make sense? Because we're at 60, go down 3 kips per foot for a distance of 10 feet, go down 30 feet, we're at 30. So, boom. Okay. Now how are we going to draw the moment diagram? How are we going to do that? We got to integrate this, right? Okay. Let's start off with this big region. Y'all remember how to get the area of this big region? Remember we take the average of these numbers, multiply it by the length. So what's the average of 30 and 150? What's that, 225? 225 times 50 is what? Right? So over here, so this is 20 feet, right? So that means this is 10 and 10. I know we're starting to get short on time, so. So that means this area of this little region right here is 1/2 30 times 10. So that's going to be what, minus 150? This little region right here is going to be plus 150. And then this little shaded region right there is going to be the average of 60 and 30, which is 45 times 10, which is what, plus 450? Did I do that right? What happens if you sum up all these areas? What is that plus that? And then if you add up these two, they're going to cancel, right? 150 and negative 150 is 0. So what's this plus this? 11,700. Have we seen the number 11,700 at some point? That's the reaction right there, right? So that reaction, when we draw the moment diagram, is going to be a sudden jump downward, right? So I am going to draw a little additional line right here because that's where we got that that 0 shear right there. And then these arrows that I'm drawing, which haven't meant much, they haven't really meant much up until now. They're going to mean a lot on Wednesday. Here's our moment diagram. So we're going to start at 0, suddenly drop down to negative 11,700. And so I'm going to be a little off on my scale because if I were to draw this hyper accurately to scale, this would be like really up here. So I'm probably going to drop this down a little bit just so we can see what's going on. So if I'm at negative 11,700 and I jump up 11,250, that's going to put me at what? 450? So what's that going to look like? Everybody watch up here. Is that going to be 1 or 2? 1. A lot to a little, right? So it's going to go something about like that. And then this is going to go a lot to a little, lot to a little, little to a lot, right? So that's going to go something about like that. So this is what value is that going to be?
0.
And that's going to be 150. And that's going to be 0. And what's so special about this value right here? That's the hinge. And what did we get? Moments are 0 at the hinge. Like I said, ignore the presence of the hinge. Look, I drew this moment diagram. I couldn't even see the beam. I sort of did that on purpose, right? I'm drawing this moment diagram. I'm not even looking at the beam. The beam doesn't matter, right? You will get 0 at the hinge because the statics will work itself out. Does that make sense? Pretty cool stuff, right? My microphone's expensive, so I'll do an eraser drop. I'm a dork, I know. Okay. Any questions? All right. So I got you practice on this one, do Wednesday. And with that, that's all I got, everybody. I'll pull the code up one more time. But I will see you all on Wednesday. If you did not get your test, stick around. I'll get it for you.